Glen Watford, Chief Engineer of GE Hitachi. Thank you so much for having me to Wilmington.
Thank you. I'm glad you could come.
Yeah, I'm especially excited to talk to you given the length of your career and experience so far in this industry. You got started off, where was it? In Florida, was it?
I went to school at University of Florida where I got a bachelor's in nuclear engineering.
Did you know that you wanted to do, did you know what nuclear was when you even first got into it? To join as a bachelor's, you had to have some...
I knew what it was. I was fortunate enough that my father worked with Florida Power and Light, was one of his customers. And I had the opportunity at an early age to go to the St. Lucie plant while it was under construction.
What did he do for them? What was his role?
He worked for Motorola, and he sold two-way radio pager systems. So Florida Power and Light was his main customer because they used a lot of
that got you some access to see some of the electrical infrastructure.
So, I think mainly we toured reactor building and then the control room at the time. I don't think the plants had started up yet. They were close to the end of construction. So I had that, but it was really an experience in college. I went as an architectural engineer initially, and there was a 1-hour course that every engineer had to take, Introduction to Engineering. Every department head would come in and talk about, this is what civil engineering does, this is what mechanical engineering does, and this is what nuclear engineering does.
That's smart. I didn't get that in college. I was a mechanical engineer, and they didn't come in and pitch the different disciplines to me.
Freshman, first semester, quarters back then. The problem is it was a 1-hour class. Yeah. It was after lunch, big, dark auditorium, and most engineering professors or deans are not necessarily the most dynamic. So listening to the civil engineering dean talk about concrete and things was maybe not exciting. So I have to admit I maybe didn't pay attention. So one day he wasn't the head of the department head was out of town, so one of the professors of the nuclear engineering department came in, Dr. Carroll, I remember it. And it's dark, I'm way up on top of this auditorium, and he grabs onto the lectern, and he launches into a Southern Baptist revivalist sermon. Brothers and sisters, I'm here to talk to you today about energy.
Wow.
And he obviously had a lot. He lit up the place, and everybody stood up, sat up and listened and paid attention. And he talked about energy, and he talked about nuclear energy and what it could do. And he was very animated, very interesting. This was 75. The industry was really getting into the swing of things at that time. And that was it. I kind of had knowledge before. I was obviously doing engineering. I like math and science, and I just walked out that day and went and changed my major. And I think within a quarter or two, I was able to start the classes because I'd already had my calculus, chemistry, and physics. And
the rest was history.
And from then on, I've been in this industry since then. I graduated a week before 3 Mile Island.
Oh.
So I was at home in Florida waiting. I just graduated. I had to go out to San Jose to GE, and I had about a month before I started, and my father calls and says, what do you know about this accident at 3 Mile Island? Of course, I didn't know anything at the time. Yeah. And
I have a question. Were people, I get that it made the public attention and that it was something scary and interesting for the news stations to talk about to everybody. And were people really upset, viscerally upset by it in the years after? It seems to me that, I wasn't there at the time, and there's this whole mythology that is formed around within the nuclear community. Oh, this is what started safety culture. This is what started the decline of the industry. But I feel like a lot of this is mythology. I would like to know, a month after it was over, did the average person even think twice about it again?
I don't think the average person did, but I think that time period of the mid to late 70s was also a time of activism.
Yeah.
So I believe locally you had a lot of local groups that looked at their neighboring utility that was now constructing a plant in their neighborhood. I think that really started to to kind of energize some of those local groups. I don't think it was nationwide. I think it was very locally sourced.
Yeah,
and
I think so too. I think few people with loud voices rather than it being actually representative of public sentiment at the time.
I think so, and I think it was part of the, some people call it NIMBY, not in my backyard. I like banana. Build absolutely nothing anywhere near anybody. And I think it went with that general kind of pushback of that time period. Yeah.
Did you start at GE straight after undergrad?
I graduated with a bachelor's degree. GE has a Edison engineering program where you can come in and do rotations where you work in an area for 6 months, work into another area for 6 months.
They had that even then, because I've seen people who are still doing that program today.
We still have that program. It's still active. It lets you over 2 years see a range of different activities. When I went, they also, at the end of that 2 years, you took classes. GE gave classes. You got college credit for that. And then we went to Berkeley, UC Berkeley, and were able to get our master's degree. So at the end of that 2 year period, I ended up getting my master's degree. And by then, I had a good idea of the areas I was interested in.
What areas were you interested in?
I was interested very much in the core and the fuel, not so much in the design, but how it interacts with the rest of the plant. Yeah. I had worked in a team that was kind of the interface between the fuel designers and the plant designers. So it was a kind of a system integration role.
Describe that interface to me. What is that?
Well, so you're generating all this energy inside the core, but unless you can remove that heat and turn it into steam, then send it down a steam line, spin a turbine, spin a generator, you can't generate electricity. So it was taking it from the nuclear aspects through the mechanicals and all of the controls, and how do all the systems interact with each other, both the normal operating systems like the control rod drives to kind of regulate the fission process, as well as the safety functions when you have to shut it down or isolate or run back flows.
It's interesting because that interface that you described, the ability to remove heat from the core, that is one of the limiting factors that determines the size of the whole system, everything, your pipe size, your turbine at the end of the day. Yep. And it's not actually the density of because you could get even more power dense than our typical reactors today, but you couldn't really probably do much with it because
the density, the power density today, I think we're about maxed out because of the 5% enrichment.
I meant theoretically you could get all
so if you go to higher power densities, you'd have to go to higher enrichment.
Or different fuels.
Or different fuels.
But we've kind of optimized based on the pipes, how water moves, all these different things. We've kind of locked in at a certain rate of heat removal from a system.
And some of that was dictated by available turbine technology. I mean, there was a benefit to simply using a turbine that had been designed for a coal plant with a certain temperature and pressure, as opposed to turbine generators are optimized to the steam flow conditions, the pressure and the flow, the blades. Sometimes they call them buckets, which probably goes back to old technology, windmills and things. But the blades in a steam turbine, the size of those blades, the pitch, how they rotate is very much optimized to those conditions.
And has that changed with newer turbine technology today? Would people design reactors that had a different temperature output, different flow rate of steam?
They can change. What's happened instead is they actually have changed because we've uprated plants as much as 20%. So significantly higher steam flows. You got the same size building, the same size turbine hull that it goes in. They've redesigned the turbines to be able to handle that higher steam flow. We haven't changed pressure, because if you change pressure now, every pipe, every component of the primary system that was designed for, at least in our case, 1,000 pounds pressure, basically. If you increase the pressure. Now you got to look at all your stress limits on all the piping. So
would people want to, moving forward with other technologies, would they want to have a higher pressure on the primary side?
We've looked at it. There's some cost benefits that you have to look at. There's trade-offs going to the higher steam pressure. And so in the new designs, we always look at that to try and optimize what is the higher pressure. You're talking percentages of efficiency. And so it really gets down to what's the added cost and what's the benefit you get from the higher thermal efficiency.
And you can only go so much higher when it comes to hitting like the supercritical point of water too, which you probably don't want to do in a reactor, right?
Yeah, they've looked at doing superheat cycles. We did a lot of testing in the 60s. We built some experimental plants looking at that. And some coal-fired plants will operate at a superheat cycle, higher thermal efficiencies, but we get into some material issues that potentially do not make it economical in a nuclear plant. But
right.
It gets looked at about every 15, 20 years to see whether or not maybe there's new materials that
have you seen that a lot through your experience in the industry? Have you seen some of these same ideas kind of recirculate every decade or so?
So one of the things I've been able to do, having been here so long and as a chief engineer, I've had occasion to go back and dig more into the history of the business.
I love history.
In 1951, we signed a contract with the government, the AEC, so that about a dozen engineers could get access to the government's classified nuclear technology for the purposes of determining what could we do to make a commercial reactor. And we studied 8 different reactor technologies. Sodium fast reactors, obviously BWRs and PWRs, boiling water and pressurized water. We looked at molten salt reactors. We looked at gas-cooled reactors. So we looked at all of the technologies that are being looked at again today.
Yeah.
Back in the early 50s, and basically did a technology down select from like 51 to 54. And ended up with 2 at the time. One was the boiling water reactor. The pressurized water reactor was already making good headway with the Navy. Westinghouse was the government's contractor. Felt a little bit like we'd be playing catch up, but in water technology, the BWR looked promising, and also the graphite moderated water cooled reactor, which happened to be what they were using at Hanford to produce plutonium.
And Chernobyl.
And at the time we were actually running the Hanford operation for the government. So we had some technology and some knowledge about that too. But, most of the technologies we see today have been looked at, but, in a lot of cases, material technology changes to make things more feasible today than they were back then. So, I think we continue to uncover what we've done in the past, and we try to make sure we learn from that and take advantage of that.
Well, I'm glad that you brought that story to me, because I'm always trying to dissect these nuclear mythologies to see what's real and what's not real. And one of the mythologies that I hear over and over and over again is, this is obviously from new reactor designers who have new combinations of fuel and moderator and coolant. The same story I hear over and over and over again is, this other combination of moderator, fuel, and coolant is far superior, but the only reason we don't have it is because Rickover told the U.S. commercial industry they could only have the PWR and BWR. But that didn't feel right to me. And what makes me think is that, no, you had the opportunity, the early industry had the opportunity and kind of ran an apples-to-apples comparison and decided on their own to go with the PWR and BWR.
Yeah, I believe that Rickover should get a lot of credit for the PWR technology and kind of shepherding that portion of the development. But outside of the PWR and working with Westinghouse, GE was off looking at completely different technologies. We were actually, for the government, doing sodium fast reactor development. The first, we did the Seawolf was actually the second submarine that had a nuclear reactor. It had problems during the trials and they converted it to a PWR, but we really worked independent of the Navy and Rickover. In fact, GE did not have good relationships with Rickover because we were focusing on commercial development at the time. In fact, when we were basically given Knowles Atomic Power Lab by the government or contracted to develop it and run it, that was in exchange for us agreeing to run Hanford. We asked for some compensation since we really weren't making money running Hanford. That was a cost type of operation to do it for the government for their program. But agreeing to run that, they allowed us to develop the Knowles Atomic Power Lab, and it was focused, its primary mission at first was on power reactor development, not propulsion, not sub. Now, by 1950, Rickover was successful in redirecting the purpose of the Knowles Atomic Power Lab, but by that time, we'd already built up a fairly substantial size commercial power group that was working independent.
And how come GE, since we're talking history, had all this kind of special access and the special relationship with the government, with the AEC? What is just GE's history in terms of involvement in military and government efforts? What role did they play?
Well, I mean, if you go back to World War II, like a lot of the heavy industrial companies, we provided a lot of technology for the aircraft carriers, for the destroyers, electrical equipment, breakers, motors, those types of things. The same for the processing, the enrichment. That was a lot of electrical equipment that was needed. And so GE and Westinghouse and a lot of other large manufacturers were part of that.
Makes sense.
As I said, starting in 1946, we ran the Hanford facility and were responsible for the reactors that produced plutonium for the weapons programs. Yep. We ran that up through the mid-60s probably. In the late 40s and all through the 50s, we were part of an aircraft nuclear propulsion program with the government.
Aircraft? Tell me about that.
Well, it was a concept to have similar to a submarine that can go out on a mission and stay out for a year or more, not have to come up and be refueled. It would be to have a set of bombers that could basically stay in the air indefinitely, using a small reactor to power the bomber. And so we worked for over 10 years on that program. There are 3 or 4 test reactors built out in Idaho that we were part of. And there was even one reactor that was flown to get shielding calculations and do that. It didn't power the reactor, but it operated in a bomber that basically went and stayed in flight for some period of time so they could, understand better what type of shielding they would need and any of those type of design considerations.
God, I wish we'd continued to pursue these lines of technology. I just think of what the world could be if all of our ocean travel, if our air travel, if our rocket ship travel got to take advantage of the incredible energy density of nuclear fuel. I mean, the world we would look in would just be so different. We'd have cities in the sky. Yeah. But that's a possibility.
Yeah.
It's almost like we have access to this magical world. We have access to this magical technology, and we just haven't embraced it yet. We just kept it guarded, and we've just stayed just a little bit away, just touch it a little bit here. But there's a whole world of potential that can still be unlocked.
Yeah, and I think if you go back and you look, there were discussions. We've got press releases where our executives are talking at the Atomic Industrial Forum about the state of the technology, and really it was about cost. Can we be competitive with the existing forms of energy? Can we take advantage of that higher power density and making sure we adequately protect the environment and the public. Can we generate electricity competitively? And in the early 50s, they were saying it would be 5 to 10 years to become, competitive. And I think in the early days, in the early 60s and 70s, they were able to accomplish that.
It was. How come? Where did it lose its cost competitive edge?
I think 1979 and the change in regulations, and if you can't design and build something in a short period of time, the uncertainties that can come in drive your cost up.
And how come the industry at that time let that happen? How come they let themselves, like other industries don't just like take additional regulation lying down? Like if I were, I'm sure that in 1979, 5 coal plants had boiler explosions across, I'm sure of it, that killed a couple people. Yeah. Like an internal industrial accident that actually killed somebody. Why wasn't the result of 3 Mile Island, hey look, something happened that we didn't want to have happen, but look at all these other systems that we already thought ahead of to incorporate that worked and made it so it was just an industrial accident that nobody got hurt in. How come that wasn't the position the industry took, and then took that to the Congress, and then took that to their lobbyists, and said, we don't want more regulation?
Yeah, my wife always says, the industry has really blown it in terms of PR and effectiveness in those areas. And I don't know if it is the fear of the unknown of radiation. I can't see it, I can't touch it. Somehow, I think just as a nation, and it's probably not a nation, it's mankind, the large catastrophic potential in our mind is much worse than the everyday you get on the road, you put your life at risk with a significantly higher probability. We accept that risk every day when we personally take that risk, and it's so much higher than the risk of being injured from most industrial accidents, and even less likely in a nuclear accident. Yeah. We just have not ever been able to successfully portray risk in a way that I think the average person can accept it.
Does that frustrate you as an engineer in this industry who's been busting his ass to make these things work better and better every year?
Yes. Oh, absolutely. And I can't tell you how much time I've spent personally with learned friends and people I meet who are fairly intelligent, I believe, and knowledgeable, that just have some predisposition to not want to either accept. I think that's part of it. And look, today corporations are trusted even less than maybe 50 years ago they would have been. Yeah. And so I've spent a lot of personal time trying to convince people. You know me, I'm fairly logical, rational, knowledgeable. Yeah. It's like, but look, today you don't trust a doctor. You trust Jenny McCarthy to tell you everything you need to know about vaccinations. Yeah. Because you can't trust the doctor because, he's incentivized to do what he's doing. Yet I like to say, he spent his whole life almost learning about this. Yeah. And so that's usually my argument. I've spent 40 years studying this.
And so tell me more about those 40 years. How many plants have you worked on? It's got to be dozens.
Well, when I came to work in 79 for GE, actively in design construction, we had 20 plants that were under construction. We were putting online somewhere between 2 and 3 plants a year at that time, 2 to 3 gigawatts a year. Electric was just from GE, and at least in the U.S., we were about 1/3 to 1/4 of all the plants going online.
We got to do that again. We got to get back up to that pace.
Well, I've seen some concern that we don't have the capacity, we don't have the knowledge.
But we did it back then. If we invented it from scratch then, how is it possible that we can't reinvent it with all the modern technology? For God's sakes, we have computers now.
We know more today. In 1960, we put our first plant, Dresden 1, online. Yeah. And, prior to that, there was no nuclear power industry. Right. And in the next 30 years, we built 60 some odd plants, 50 gigawatts of electric, I believe that if you build it, they will come. There's a lot of smart technology out there. To be honest, our industry, the requirements really are no different than other industries. We have to do more paperwork. We have to do more, confirm it and document it. But the fundamental design is the same. The design process we use is the same. The testing and qualification we do is the same.
And how similar is a nuclear plant to, let's say, a coal plant?
90% of the plant has nothing to do with nuclear. It is a steam-powered power plant with steam lines and turbines and generators and condensers and circulating water pumps and feed water heaters, pumps and valves. We've looked at it in the past. We have between 10 and 20% of our workforce are nuclear engineers that need to know about fission and all of that stuff. We have mechanical engineers, electrical engineers, civil engineers, structural engineers. That's the majority of the engineers that we have.
And then, sorry, I'm going on a riff with you here, but then how come it's not as simple as hire the coal plant company to build a coal plant and just say, oh, but don't put in the boiler yet. Just hold on for the boiler. I mean, they can build these things in less than 2 years now. They build them anywhere in the world. They build them at the gigawatt scale capacity. How come we don't just hire the coal plant to get all the way up to the boiler, and then we hop in with, I mean, how much is inside the nuclear island? Some concrete, some more pipes, some so a big vessel, but vessels can be manufactured like anything else. Why is it more complicated than that?
Well, I think it gets back to the regulations and the coal plants. The only protective devices they have is to protect the equipment, right? To prevent a piece of equipment from maybe going into a condition where it's going to destroy itself, which would be an economic loss for the plant. That's the main set of requirements. There are pressure, temperature limits, for piping.
But what's ironic is that has probably driven extremely high levels of safety performance. The fact that they have the economic incentive to protect their own equipment and not have an equipment failure. That means they get to use digital technologies, they get to use the most advanced sensing, they get to use, because that is their motive, they're probably doing a better job at safety because they've done that.
Our industry is reluctant to change. The industry, the regulator, the utilities, the vendors, we have almost trained ourselves to resist change. There's a fear of change, and it's irrational, I believe. It is driven by the perceived cost to make the change. Some of that is regulatory driven. Sometimes we do that to ourselves. But digital is a great example where it's almost, for this versatile test reactor we're planning to build for the government, we have actually gone to an analog protection system because of the perceived added cost to license a digital system.
And nobody's going to the regulator and saying, we know that your number one concern is safety. Ours is too. You are making it less safe by making us more conservative when it comes to adopting digital technologies. Like, cut it out. Like, let's come to a compromise. So long as we use a electronic control device that's used in 100 other industrial plants across the world, we want you to rubber stamp it. We don't need you to come in and look at every line of code. Like, other industries have already perfected this. Is anyone having that conversation?
The utilities and the industry have had those conversations, especially on digital upgrades, and they've basically shown the case to the regulator that we've actually ended up not necessarily making the plants less safe, but prevented them from being safer with this new technology because of the regulation. There have been some relaxation. Again, you have to recognize the regulations are written at a very high level, and it all becomes, how do you demonstrate you've met them, which is not necessarily as quantitative and demonstrative. It sometimes becomes one regulator's opinion versus another's. And it ends up being, will they ask enough questions where eventually time goes and it becomes cost prohibitive because they just continue to ask questions. And I believe the newer plants that have been licensed in the U.S., the Vogels, the ESPWR, our design, that has been an attempt to streamline that regulation process and make it less let's say, qualitative and avoid having that cycle of questions and answers from the regulator. We haven't gone through it enough. We suffer from a lack of scale.
Yeah.
When you're building 1 or 2 plants in the U.S. right now, which is what we're building, you don't have the opportunity to go through that process and cycle it and refine it and improve it. And so same with the coal plants or gas-fired combined cycle plants. They're building hundreds of them, thousands of them. They can get the economies of scale.
Yeah, there's a certain experience to building something and that experience itself helps you bring costs down, helps you increase safety as well.
Repeatability.
And I feel like in the airline industry, you can do certain things like even like test pilots, and you fly over a farm field somewhere, and the guy's got a parachute, and like so worst comes to worst, and you can test out different concepts with how does this foil help you maintain balance in your aircraft and stuff. Is there any equivalent like that, or could there be any equivalent like that in the nuclear industry where you get to say, listen, in order to be better, we need experience building. If we build them in a mine shaft, can that be our experimental test flight? Can we just do whatever we want as long as it's in a mine shaft?
Well, I think we've had a good history of building test reactors at the national laboratories. Usually they're very remote. Right. Idaho is the most common place. And we built a number of reactors and successfully operated them. The entire, a lot of the history of the PRISM sodium fast reactor, which is the basis of this new versatile test reactor, that was based on EBR-2, experimental breeder reactor number 2, that was built, that was actually at Argonne and operated for 20, 30 years. So, we've had experience doing that in the past. Again, I think that gets to a concerted government-sponsored development program to support the industry. I don't think energy is something that's well handled by just the free market. The cost of entry is extremely high. Yeah. We've got 50, 60 reactor concepts floating around a number of different small startup-sized firms. We had that in the 50s and 60s. The companies that were involved, you probably wouldn't know. You probably wouldn't recognize a lot of the names that were around back then that were looking at the different concepts, because eventually it narrowed to just a few. Yeah. And I think it's just the cost and the scale. You can't do it as a small startup. The capital involved is significant.
Was there another round of this? So in the 50s and 60s, they tried out all these different reactor types. Now, certainly, I hear, I can name 50 or 60 companies right now, every different combination. Right. Was there something in the middle too, where there's another period of let's experiment?
In the 90s, that started up again.
Okay, interesting. What happened then?
There was DOE funding for, I think it was actually a post 3 Mile Island that, we're stuck on what a lot of people will call the Gen 1 or Gen 2 reactors, the water technology. We all believe there's better technology that's maybe safer, that has more advantages to it. And I believe there were rounds of government fundings to try to bring the sodium fast reactors, high temperature gas reactors, molten salt, the whole Gen 4 process, probably the early 2000s. It tends to come in waves, and a lot of things, happen that way. It's never been continuous. It's been kind of up and down. Yeah. It's possible the events in the industry, 3 Mile Island, Chernobyl, Fukushima, have kind of turned it around from time to time, that we can't seem to ride through those different events. But yeah, there's continued to be technology development.
And what's wrong with water-based systems themselves?
I don't think there's anything fundamentally wrong with water-based systems. I think there's the ability to make them just as inherently safe as others. We're working on BWRX 300, which is a small modular reactor based on the BWR technology, very passive. We believe we can get the cost actually down to a competitive basis. A lot of it are licensing and regulatory type hurdles that we are working hard to overcome, to be able to demonstrate that it is safe enough that it doesn't necessarily have to have all the added features.
And why not just build it in Uganda, where they don't even have a regulator? And obviously you're not going to build something that's not safe. It's not like the NRC is teaching you how to make it safe. You're going to make it safe however you design it. So why not just skip the whole regulatory hassle at all, build the same thing you would have built here, but just build it in Uganda and not have the $1 billion price tag.
Ultimately, you've got whatever the local regional politics are that you have to deal with.
Certainly, that's like in Uganda, it's like a $5 million problem. You hire the head of government, you hire his son to be your chief lobbyist, and $5 million, you got the whole thing solved.
We tend to not work that way. We can get in trouble as a
sure,
as a
but
public
you know what I
company.
mean. Yeah, it's like or a $5 million marketing campaign. Make Ugandans love nuclear so much that it's not even an issue.
And we've been talking with countries around the world. I believe that all will follow the IAEA kind of general requirements, and you see that in the UAE. They've adopted that. So I think as a public company, nuclear liability protection is obviously an important thing. It's a huge bet for a company to do that. You want to make sure you're in a regime where the liability laws are acceptable, because you've got shareholders that want to make sure you're protected. But we continue to look at other countries as a way to actually have a development space. The Saudis are talking about, moving into this. We've had discussions in Africa, in different countries. It poses other challenges, because typically a country is going to want to establish their own nuclear kind of industry or regulatory approach. And then you've got a lot of education that you have to go through, and then the experience.
Yeah.
So some of the models would have you take a U.S. operating company who operates a plant today. They would team with an NSSS vendor, and they would propose, and we've done this in a couple of places, kind of a combined, we'll design and build it, and our utility partner will operate it, and then train you, and then over time basically turn it over.
So what are some of the things that you've seen in all these different plants that you've been a part of that, now that there's this opportunity to kind of build the next generation of a BWR, what are some of the design features that specifically based on things that you've seen from the old plants that you want to incorporate in the new one?
Well, I think if you go far enough back, the plants were much simpler. And design principle number one is keep it simple.
Yeah.
I
keep
would
it
say
simple,
keep it simple, stupid.
Yeah,
Right?
that's what I learned in school too.
The more complexity, then more things that can go wrong, the higher the cost.
So what are some areas of simplification then?
Well, the direction we've headed to simplify the BWR is to go to natural circulation, eliminate the recirculation pumps that pump the water.
Which is how it used to be back in the 60s.
Our first design was a natural circulation board.
Great.
Back then though, we couldn't get enough flow through the reactor. We couldn't get a high enough power density to make it economical, so we went to forced circulation. It was less expensive to do that. Now with better materials, just better understanding of the thermal hydraulics, different designs of the pressure vessels, we can get the flows and the fuel, we can generate the higher power density without forcing more flow through it.
So what does that mean? How does it help me paint the picture? So you have a higher power density. So that means what? You're boiling water at a faster rate. Is it creating a higher pressure of steam at the top of the?
It's not necessarily
reactor?
Higher pressure of steam, but natural circulation operates on the fact that the density of water inside the core is low because you're boiling. Right, so you just have less atoms of hydrogen and oxygen, so it's less dense. And your colder feed water that's in an annular region is dense and heavy, and so it's just a gravity head. It pushes down, the density head pushes down and drives the flow just in a natural circulation loop.
And then, okay, so then that creates your steam, and that steam then still goes through some stuff to get rid of the
dry it up a little bit. Yep.
Then it goes through your turbine.
Yep.
And then on the other end of the turbine, you still have your condenser that creates a vacuum.
Condense it, create a vacuum. Then you have pumps that pump it back up to pressure, the feed water pumps basically. And you heat it back up for thermal efficiency purposes. You steal some of the steam from the turbine. You actually don't send through the turbine. You use it to heat the water up.
Oh, cool, yeah.
There's the laws of thermodynamics that make it more efficient to do that.
How come you waste that good steam, which is already at the high temperature and pressure, to heat up your water before it goes back in the reactor, instead of just like wrapping the pipe around the reactor and then through the walls of the, just through convection capture
it's
heat
just
of that way?
there's fundamental, it's called the Rankine cycle. There's just fundamental thermodynamic properties with the enthalpy where it is better, instead of using the nuclear heat, it is better to use that steam to preheat the feed water to a certain temperature. And there's a optimization that's done on what's the best temperature
and then
to heat
that flows back into the reactor.
Back into the reactor. Now it's much cooler.
And what's the pressure when that goes back into the reactor?
Well, in a BWR, it's 1,000 pounds, roughly 1,000 pounds of pressure, PSIA.
Oh, so it does have a pretty high pressure, even though it's got to be like, when it comes into the condenser, that's got to be like zero.
Well,
pressure,
it's low,
right?
yeah.
Or something low,
yeah,
right?
It's so very low.
So then there's a lot of adding pressure to it. And
that's pumps,
done through
the condensate pumps and the feed water pumps then pump it back up to the pressure to go back into the vessel.
I see.
Right.
Got it.
Right.
And so when it's injected back into the vessel, it's already at a higher temperature, higher pressure.
Right.
Less of a thermal shock, I guess.
Yep.
To
well, and it part of it's thermal shock. The other part is just efficiency, because, I'd like to use most of the heat of the reactor to generate the steam.
Yeah.
If the water's coming in too cold, so to boil at 1,000 pounds, I have to be at 540 degrees Fahrenheit.
I see.
If my water's coming in at 100 degrees Fahrenheit, I've got a lot of heat just to get it to start to boil. So instead, it comes in at maybe 420, somewhere around there. So we're only having to heat it a certain amount.
You almost wonder if there's like efficiencies to be gained, if there's like waste heat from another process to get it back up to temperature a little bit.
If it was in conjunction with another plant that had waste heat, you could use that heat potentially to as a feed water heating. But ultimately, this whole concept of natural circulation, the benefit is, one, eliminate pumps and pipes and valves. But the big challenge when you have a vessel, then you have nozzles and penetrations and pipes coming off of it. It's the risk of, what if one of those pipes break, right? So now I'm losing my
Has that
coolant.
ever happened? This whole Loca thing that the industry is so terrified of, has that ever happened? A large break
Not
Loca?
the large break Loca.
So why, I understand how the risk metric was initially developed. I get that you want to look at the worst case scenario and then you say, okay, let's try to mitigate that.
Right.
But over time, as they've re-examined that principle, it seems to me that that's really not how you want to design your system, based on the unlikeliest thing, even though it's the most disastrous, especially given that we've got in the case of an accident, we do have other ways to mitigate the hazard that might come from it. We got the extra sprinklers, we got this. It seems to me that no longer should we be designing our entire plant around this large break Loca that's never happened, is just theoretical, and is now driving design decisions and costs throughout the system. Right. Has anyone ever pushed? I mean, it seems like with these integral reactors, people are designing even more to satisfy the large break Loca risk. Has anyone ever pushed back on that and said, forget about large break Loca, we don't want to do it this way, it's unlikely to happen, we're safe enough with other systems in case something does happen, let's design a system not accounting for it?
Yeah, I believe that the current advent of risk-based licensing gives you the ability to do that. To date, the only way that has been done is through design, not through just a risk-based argument that says, if I really look at what's important, it's not the large break Loca. And so if I define my design basis events, that probably goes away. My station blackout becomes probably my most likely event from a probability.
Designed from a station blackout.
Oh, yeah, by the way, it's happened.
Yeah.
And how would I design it according to that?
Yes.
Some of the newer plants are being designed that way. However, they're being designed that way also. They've eliminated the having to justify it, because fundamentally you eliminate all the large penetrations that are low in the vessel, so you eliminate the possibility of it. we have yet to go in and actually attack it and say, this is not a credible event. It really should not be the primary one. I can look at that scenario and show with reasonable assumptions that I'm able to ride that out. But my design is more focused on removing heat as opposed to pumping in more water.
Yeah.
The regulations are there to support that, and we are applying that on BWRX 300. We're approaching it from a risk-based perspective. But it's almost our ace in the hole is, and we don't have any penetrations in the vessel that could even conceive of, since they don't exist, then I don't have that possibility too. I think down the road, as that process of risk-based design comes into play, I think there's a possibility to further improve the designs and come up with newer designs with different assumptions that we can show are safe or safer, and hopefully then lower the cost. But we believe on the BWRX 300, there are other benefits from having it be natural circulation in terms of just lower cost with fewer pumps and pipes and valves and fewer components. We can make the containment smaller. Most of the cost is really in the volume, the concrete, the steel, the size of the building, and the amount of time it takes to construct it.
And why don't people go after that when thinking about new designs? Once again, this is always my pressure test. Why not just say we don't want containment, we're just going to put it in a mine shaft, or not even mine shaft, but there's other geographic situations you could imagine. Inside of there's all these things.
They're typically not located close enough to a population density.
Right,
that
I'll take my 10% efficiency loss on transmission.
On the transmission.
Any day of the week to get a 50% capex reduction. Or something. You know what I'm saying?
But I don't know that our transmission and distribution system is set up to where it would even be able to handle that.
Yeah.
So I think we're trying to play the game of design is all about optimization and trade-offs, right? So the whole concept on BWRX 300 is we are trying to optimize on the power level and the pressure and the supporting systems that will lead to the smallest containment, the fewest number of systems. And we're making some systems a bit more complex because they don't add a lot of cost, yet they allow us to greatly reduce the cost of the containment. We will have probably a fairly complicated reactor pressure vessel system because it will allow us to make the containment smaller.
Tell me about that more.
And we're still developing that.
Okay. Well, you just piqued my interest.
I don't know, all the patents have been filed. And
finally, someone's going directly after cost. Tell me everything.
Trying to maintain our competitive advantage.
I don't think anyone else is going out there building 300 megawatt BWRs, but
that is true. That is true. But there's still technologies that we're trying to implement and determine that they're feasible and will allow us to do that. Working a lot with AEs and constructors on different techniques for how can you build this. It can't take this long to build a plant.
What's your target? Yeah, what's your target construction?
I don't know what the target construction is, but I know we've built plants in less than 48 months.
Yeah.
And we'd be shooting, that's
in the 1970s we did that with 1970s construction technology.
I believe in 90s we did that. The ABWRs we built with our partners Hitachi and Toshiba in Japan, we built those in roughly 4 years.
Yeah.
And so we believe we can reduce that. These will be smaller plants.
Even smaller. What do you think? Yeah. If you were to say you're wishful thinking, what's achievable? What do you think is achievable?
I would think you can do it in 2 years.
Yes.
The size of the plants that we're talking about, that should be our target.
Yes.
We are doing all of it. We're designing the cost. Yeah. We're looking at it and say, this is what we project the market will be, where we need to be competitive. And that is our design parameter.
Why not lock that parameter in and tell the engineers that this is what you have 2 years. If you cannot convince me that this thing is going to get built in 2 years and convince me you're out of a job, put the pressure on them. Because that's what it takes. It takes being, because I mean, listen, I've led teams of engineers before, and they'll always find, oh, we need this extra thing, this extra component, this extra efficiency. Oh, we can use this super duper cool tractor to move the dirt around. There's always something extra. But I feel like sometimes you just gotta lock it in and say, no, you get 2 years, that's it.
So, change control is number one issue of design process, is how do you control changes? And a big part, and we see this working with INL, on this versatile test reactor, is what's the mission? They are very focused on what's the mission, and every potential change or new design is measured against the mission. Does it support the mission? And like I said, in the case of the BWRX-300, the mission is get to be a certain competitive cost number. And so anything that drives that in the right direction is acceptable. Anything that drives it in the wrong direction, go back to the drawing board.
And tell me more about these conversations that you're having with the architect, engineers, constructor companies. What's it like? What are some things that you've learned that maybe you didn't even consider before?
Well, what we're trying to do is look outside the nuclear industry and say, how do other people build large structures, complicated structures? What are the different techniques? A lot of these plants are underground. A portion of them is underground. The excavation and the pouring of the concrete and the rebar and all that is a large part of that cost. So who else are building underground structures, and how are they doing
How do you do that? I guess like subway stations maybe? Who else?
Subway stations, tunneling technologies, what are the different ways? Could you, how much of it can be pre-built? So the whole concept of modular, we've done modular kind of at a high level in the existing plants, the ones that were built in the 90s, very, very large portions, but they were pretty much from a ground up type of assembly, a lot of, large Lego blocks brought together and assembled, less work done on site. How much more could you actually assemble and then basically put it in place? Or those are the challenges that we're working on.
Amazing.
Yeah.
What are some of the other things that we should stay tuned about, be excited about, some of the other work that you're involved in right now?
Well, I think that our focus right now really is twofold. One is the BWRX-300. Can we make a cost-competitive design using the BWR technology? I think the success of working with the DOE on the versatile test reactor is important. It's important in the U.S. to kind of renew the ability to do the types of testing that we need to do. Those are our two key focuses. Obviously, we're working to keep all our plants operating safely, efficiently. We continue to drive improved fuel efficiency. We want the plants to continue to operate that are operating now. We think that's important. And we have to help them keep their costs down. We need that fleet because that's the generation of operators and maintenance organizations that will then seed the future plants. So it's really all about keeping those plants operating as efficiently and cost effectively as possible to bridge, getting the new technology, getting the government's programs going where we can support the industry. I think those are the key things that we're focused on.
And as someone who was inspired by nuclear when they first heard about it, paint us your picture for why this is important moving forward.
Well, I think most people in the nuclear industry very much believe in its benefit in terms of, being part. I'm not a proponent, and I see it all the time, and I don't like it. Nuclear is the only answer. I don't believe in that. I never believe in someone brings me a single solution. I believe it is part of the solution. I think it is a key part of the solution. I think I saw something the other day, a third of the, of the clean emission technology is powered by nuclear power today in the world, and I think that is important. I think with 7 billion people on this planet, we need all sources of electricity. We need clean sources of electricity, and nuclear has a key advantage, having the high energy density and the small carbon footprint. I just don't think you can do it otherwise, and I think Germany is proving that to the world every day with their lack of progress on reducing their emissions as they close down their nuclear plants. So I just want to make sure it's not the only solution, but it's an important part, and that's what I try to advocate.
Glen Watford, thank you so much.
Thank you. Enjoyed it. Thanks, Brett.